Simple random samples. If you're going to take a sample, you want it to be a simple random sample. Why do you want it to be a simple random sample? Because we're going to have to use our sample to reason about some population. The sample represents partial information about that population. And in order to do probabilistic reasoning about this population, I have to have a probabilistic model of where the sample came from, how that sample was produced. And a simple random sample is the sort of simplest probabilistic model, in a sense. So, the idea is very simple. Simple random sample. Okay, it should be simple. The intuitive idea of a simple random sample. Take everyone in the population, put their names into a hat, mix them all around in the hat, choose names from the hat one at a time at random with replacements. Mix all the names, pull out a name. That's the first person in your sample. Put it back. Mix all the names, pull out a name. That's the second person in your sample. Put it back, etc. Notice that we're doing sampling here with replacement. So you could get the same person repeated in your sample. That could happen. That's a very nice thing mathematically when it comes to working out the mathematical theory of how we estimate things and if those estimates are accurate and why. It's very nice to do the sampling with replacement and to have this property. You'll see why in a second. But in practice, sometimes sampling is done with replacement, sometimes without replacement, and most of the big results and methods we're going to develop in the rest of the course, they work in either case. Cool, but we're only going to discuss simple random samples with replacement. So we could have the same person appearing multiple times. Now, we've got to mathematically formalize this simple idea. How do we do it? Well, let's define a random variable, capital X, which represents the value we're trying to measure, be it someone's age, someone's shoe size, whatever it might be, some numerical property. And this random variable X represents the value of that numerical property on a randomly selected member of the population. All right? Then, if I'm taking a simple random sample like this, and I look at the first person in my sample, well, that person is equally likely to be anyone in the population, right? So if I measure that same property on this person, the distribution is the same as the distribution in the whole population because this person is equally likely to be anyone in the population. So say, for example, just to give a really concrete example, suppose that 3 of these people have shoe size 10 and these 2 have shoe size 8. So these 3 have shoe size 10, these 3 have shoe size 8. Then in the population, what's the probability of getting capital X equals 8? Well, 2 out of 5, right? If this person is a randomly selected person from this population, what's the probability that his shoe size is 8? Well, 2 out of 5, because he's 1 out of 5 chance of being this guy, 1 out of 5 chance of being this guy, 1 out of 5 chance of being this guy, and so on. All right? So, if I let capital X1 be the value of the thing I'm measuring, shoe size in this case, for the first person in my sample, and capital X2 be the value of the thing I'm measuring for the second guy in my sample, well then each of these guys, capital X1 and capital X2, if each person is a randomly selected person from the population, the distributions of each of these random variables should be the same as the distribution of X, right? And moreover, if I told you the shoe size of this guy was 8, that would not influence your beliefs whatsoever about the shoe size of the second person in my sample. Because we're sampling with replacement, right? If I was sampling without replacement, then it would, certainly. But if I'm sampling with replacement, each of these people is just a randomly selected person out of these 5. And so the distribution of shoe sizes is the same for both. And if I tell you this guy's shoe size tells you nothing about it. It might even be the same guy, right? The distribution, this guy has a 2 out of 5 chance of having shoe size 8. This guy also has a 2 out of 5 chance of having shoe size 8, regardless of this guy's shoe size. Okay. So, formally, what we just talked about, a sequence of random variables, x1, x2, up to xn. This is the usual notation. This capital X represents the distribution of the thing I'm measuring in the whole population. Capital X1 represents the distribution of the thing I'm measuring in the first of my sample values, capital X2, and the second of my sample values, and so on. So a sequence of random variables x1, x2, up to xn, which represent the values of the people in my sample, is a simple random sample, just abbreviated SRS, usually because it takes too long to write simple random sample, with replacement if, well, each of these random variables has the same distribution as the population, and the sequence of random variables is independent. Right? So this means that if I give you any information about any number of these sample values, it doesn't change the probabilities of any of the others, taking any values. Cool. And so that's exactly what is explained up here, right? Okay. And so the really fancy way of mathematically talking about simple random samples is to say that the random variables xi form an independent, identically distributed sequence. So that's, if you put these two properties together, they have the same distribution and they're independent. So it's abbreviated IID. It comes up so often. Independent, identically distributed sequences of random variables. Why does it come up? Because that's a simple random sample. Okay, and when people say random sample, they usually mean simple random sample. This is, again, just like with when we had uniform distributions. When people say select a random number between 1 and 10, random has a colloquial meaning as well as a precise one. Well, that's the point, is that it has a colloquial meaning and we don't want that to kind of confuse this precise thing we're saying. So that's why we used to say select a number uniformly at random between 1 and 10. If you want it to be, select a whole number uniformly at random between 1 and 10, then I'm really saying I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 with equal probability. Same idea here, okay? I want to say a simple random sample to really emphasize that it's a very precise thing. It's not just I'm just willy-nilly selecting people at random, quote unquote, whatever that means. No, it means exactly this. It means that each person in my sample is equally likely to be anyone in the population, and knowing who any number of these people are doesn't give you any information about who the others are in your sample. Great. Okay, and I want to point out that this is, from a theoretical point of view, this is the best possible kind of sample, because it's going to make reasoning probabilistically about properties of this sample as easy as possible, as easy as it could possibly be. Because every single one of these has the same distribution, so I'm really only ever dealing with one distribution, and it's the population distribution, which is the one I want to know about. And everything is independent, so when I go to calculate probabilities, I can multiply probabilities without considering any conditional probabilities. It's going to make everything as easy as possible. And lots of the statistical methods, standard statistical methods, are built on this assumption that you have a simple random sample. And that is the most violated assumption in statistics, okay? There are lots of ways people do statistics badly, but that assumption is a super idealistic assumption that is almost impossible to satisfy in practice. Give you a really simple example, and then I'll give you a more complicated one, okay? Kind of a current one. Suppose that you wanted to get a simple random sample of, let's say, just say that you're doing a project at the college and you want to estimate something. Say you want to estimate the number of hours someone studies for just a randomly selected student at Champlain College. Well, then in order to do that, you need to make sure that when you select the people for your sample, you have an equal chance of getting every single person who's studying currently at the college. Now, you as a student really have no way of doing that, right? The only way that could possibly be done, this would be a nice service actually, but see, okay, there's more problems here, is that the administration actually has a list of everyone who's registered at the college, and they could go through that list, and they could have a computer pick someone at random from that list. They could actually get a randomly selected student who is currently studying at the college. But you cannot, because you don't know the set. You have no idea who these people are. The set of all people, that's a lot of them, who are currently studying at the college. So you really have no way of obtaining a good sample, a simple random sample. Even if you went to the administration and you asked them, hey, give me a randomly selected person at the college, You have to contact that person, and if that person doesn't respond, then your sample is no longer a simple random sample. You can keep trying until you get people that respond, but then you're biasing your sample, because then you're more likely to have people in your sample who respond to requests for information. And it's going to bias your sample, because certain types of people will be less likely to respond, and certain types of people will be more likely to respond. And you don't want that. That's more probabilistic information that's not taken into account. And here it's going to make the probability calculations we do not right. Okay. More difficult, more subtle example. Think about this current context where all the stuff about COVID-19 is not known. In particular, think about let's just pick one, the percentage of asymptomatic cases, so the people who contract the disease but don't show any symptoms. Now, suppose you want to estimate that. What's the probability that someone who contracts the disease doesn't show any symptoms? What we're going to see later in the course, is that you can get a surprisingly accurate estimate of that number with a surprisingly small sample. However, the issue is the quality of the sample. If you could get a simple random sample, that would be amazing. You would only need a few hundred people in your simple random sample. You could get a really accurate estimate of the rate of asymptomatic cases. However, think about the issues around that. What is this? What is the population in that context? If you want to estimate the rate of asymptomatic cases, well, the population consists of all the people who got the disease, right? You want to take a sample of people who you know contracted the disease, and you want to figure out in your sample the proportion of them that didn't show symptoms. So this population, this is the set of all people who contracted the disease. How do I get a random sample of people that contracted the disease? I can't. Because lots of people who contracted the disease never even knew they had it. So these issues are really big and really difficult issues. I linked this paper on Leia about estimating the rate of asymptomatic cases from the people on board the Diamond Princess. And this is a really good idea, because this Diamond Princess cruise ship, everyone was stuck on the ship. And so this is a situation where you have a bunch of people a bunch of people on the ship, and every single person was tested when they got off the ship. Or maybe before. Anyway, the point is that every single person was tested. And so you can really think of this sample. You can say, okay, I now have data where I am really randomly selecting from people who are on the ship and who had the disease. I'm really getting a higher quality sample for this purpose because I have a better idea of this population, right? Because I'm really selecting people from a group of people who I know had the disease. Okay, all the people on the ship who were all tested, and I look at the results and I say, okay, of the people who were tested and it was determined they did contract the disease, I can say, okay, how many of those were asymptomatic? That's something that's impossible to do, for example, in a whole country, because the majority of people who contract the disease are never tested. And so if you were to try and do this in a whole country, the only people here you would ever see who would appear in your sample, these would be the people who had really bad symptoms. Because the only people who go to the hospital, the only people who get tested are the ones who have really bad symptoms. So it's really hard to get an idea of how many people got the disease but didn't show symptoms.